So in this problem, we're investigating maximums and minimums for the function f of x equals 4 minus e to the negative x minus 2, the quantity squared, on negative infinity to infinity. Now, because this is not a closed bounded interval, we lose the guarantee of having a global max and a global min. So we'll have to see what happens as we look at this function. Now, our first step is going to be pretty similar as far as we're still going to take the derivative of this guy. Derivative of 4 is 0. A derivative of an exponential always has itself in it, negative e to the negative x minus 2 squared, times the derivative of the input, which is the exponent. So bringing that 2 down, we'll have a negative 2 times x minus 2, leave the inside alone, decrease the power by 1, multiplied by the derivative of the inside, which is just 1. So our derivative, let's clean this up a little bit. We got a negative times a negative, so that'll be positive. So we'll have 2 times x minus 2, and then our exponential piece, e to the negative x minus 2 squared. Now, we're going to set this derivative equal to 0 to see if we have any critical points. One of the things to always remember about exponentials, this part here will never be 0. In fact, it'll always be positive. We'll use that fact in a minute here. So the only thing that can be 0 is going to be from right here. That's the only part where we might get a 0 from, and it's going to happen when x is 2. So we have a critical point at 2. So let's build our sign chart from this. Now remember, this is always positive, so if x is larger than 2, say 3, this will be positive. A positive times a positive is positive. So our derivative is positive, which means from 2 to infinity, our function is increasing. If we use a number smaller, say 0. 0 minus 2 is negative. A negative times a positive is a negative. So our function is decreasing. So right now, we can definitely conclude that we have a relative minimum at x equals 2. Now, what we know of this function is it's decreasing to 2 and then increasing after 2. It's always decreasing before 2 and it's always increasing after 2. So not only do we have a relative min at x equals 2, we're going to have a global min at x equals 2. We'll look at the graph here in a second, but because it's always decreasing to 2 and then increasing afterwards, we know not only is it a relative min, but it's going to be a global min. Now, to figure out what that global min is, we need to evaluate our original function at 2. So 4 minus e to the negative 2 minus 2 squared. So that's just e to the 0, which is 1, so 4 minus 1, or 3. So we have a global min at the point 2, 3. Now the other thing we'll do is we need to see if there's any kind of maximum going on here. Well, there's no other critical points, so there's no local max. Let's see what happens as we take the limit as x goes to infinity of f of x. As x goes to infinity, this exponent's going to go to infinity, so that means e to the negative exponent, we have our decreasing exponential function, so this whole piece here is going to go to 0. So it's going to be 4 minus 0, or 4. Similarly, if we go to negative infinity, we're actually going to have the same limit because the exponent's being squared. So it doesn't matter if x is going to positive or negative infinity because it's being squared. It's going to make this whole thing positive, and this is going to make it back to a negative again. So this will also go to 4. So we've got a horizontal asymptote at 4, something that the function is going to approach but never actually equal. So we do not have a global max or a relative max. If we were to take a look at this function right here, we can see that what we found is confirmed. We see the horizontal asymptote at 4, and we also see this relative minimum, which is also a global minimum, at the point 2, 3. So We did lose the guarantee of having an absolute max and an absolute min. That does not mean that there isn't one. We just have to do a little bit more analysis than just checking the critical points and endpoints because we didn't have a closed bounded interval.